What does it actually take for humans to reach Mars? The first thing you would probably notice about a trip to Mars is how quickly the idea of distance stops being an abstract number and starts becoming a physical reality. From Earth, Mars looks like a bright reddish object that you can point to in the night sky. And because we have spent so much time sending spacecraft there, it is easy to develop the impression that Mars is practically next door. But once you actually begin planning a human mission, that illusion disappears very quickly. The Moon can be reached in roughly 3 days, which is why the Apollo missions could leave Earth, land on another world, and return home within a relatively short period of time. Mars is completely different. Depending on where Earth and Mars happen to be in their orbits, the distance between them can change enormously, and even when the planets are relatively close, a crew would still be facing months of travel. A realistic journey, using the kind of propulsion currently being discussed, would take roughly 7 months each way, which means the first human mission to Mars would not be a short expedition, but a multi-year commitment. And that one fact changes almost everything about what it means to go there. Mars has fascinated people for much longer than we have had the ability to reach it. Early astronomers could see it moving against the background stars, and as telescopes improved, the planet began to develop features that made it look surprisingly familiar. There were polar ice caps, changes across the surface, and what appeared to be seasonal variations. In the 19th century, observations of supposed channels on Mars helped create the idea that an advanced civilization might have built an enormous network of canals to transport water across the planet. That interpretation turned out to be wrong, but it revealed something important about the way we have always viewed Mars. We wanted the planet to contain something. We wanted it to be inhabited. And even after robotic missions transformed our understanding of the Martian surface, that fascination never really disappeared. The question simply became more scientific. What happened to Mars? Why did it lose so much of the environment it appears to have had earlier in its history? Where did its water go? And could anything resembling life have survived there? Those questions are part of the reason Mars remains the most obvious candidate for humanity's first major expedition beyond the Earth-Moon system. The other reason is that Mars is relatively close. That word, relatively, is doing a lot of work here, because tens of millions of miles is still an almost incomprehensible distance for a human being. At their closest, Earth and Mars can be around 34 million miles apart, while the average distance is roughly 140 million miles. Mars also takes about 687 Earth days to orbit the Sun, compared with Earth's 365. So the two planets are constantly changing their positions relative to one another. You cannot simply launch whenever you feel like it and point the spacecraft at Mars. Mission planners have to wait for the geometry of the solar system to become favorable, and useful launch opportunities appear roughly every 26 months. Miss one, and the next opportunity may not come for another 2 years. That means a Mars mission has to be prepared around the movements of the planets themselves. The spacecraft has to be ready, the crew has to be ready, the supplies have to be loaded, and the entire mission architecture has to be capable of taking advantage of that narrow opportunity. The solar system does not adjust itself around human schedules, so humans have to adjust themselves around the solar system. And this is where a Mars mission begins to differ from almost every expedition humans have ever undertaken. On Earth, if something goes wrong during a journey, there is usually some possibility of changing the plan. You can turn around, find another road, land at another airport, call someone, or simply stop. A Mars crew would have none of those options. Once the spacecraft has departed Earth and committed itself to the interplanetary trajectory, the crew is entering an environment where distance itself becomes one of the primary hazards. Even communication is no longer immediate. Radio signals travel at the speed of light, but light still takes time to cross the enormous distance between the planets. Depending on where Earth and Mars are in their orbits, a signal can take somewhere between roughly 3 and 22 minutes to travel one way. That means a crew member cannot have a normal conversation with mission control. If something goes wrong, the astronauts may have to explain the situation, wait for Earth to receive the message, wait for experts to decide what to do, and then wait again for the instructions to reach them. The people on Earth could be working on the solution, while the situation inside the spacecraft has already changed. We got a taste of that problem when Perseverance landed on Mars in February 2021. Engineers on Earth could not simply watch the landing and intervene if something started going wrong. The communication delay made that impossible. They had to wait for the spacecraft's signal to arrive and tell them what had happened. For a robotic mission, that is stressful enough. For a crewed mission, it becomes one of the defining characteristics of the entire expedition. The astronauts would have to be capable of handling problems themselves, because Earth would no longer be a real-time emergency service. Mission control would still be incredibly important, but it would be advising from a distance rather than directly controlling events. Before any of that can happen, however, the crew has to leave Earth, and the scale of that first step is easy to underestimate. A Mars-bound vehicle has to accelerate a large amount of mass away from Earth's gravity, and most of the mass involved in a large rocket is not the crew or the equipment they need. It is propellant. The Starship architecture discussed for future Mars missions illustrates this brutally well. The full vehicle is roughly 120 meters tall and, when fueled, weighs around 5,000 metric tons. The Super Heavy booster is designed to generate roughly 74 meganewtons of thrust at liftoff. Those figures are so large that they stop being intuitive. But the basic point is simple. Getting people away from Earth requires an enormous amount of energy, and most of the rocket exists to provide that energy. Inside the crew compartment, the launch would be an extremely physical experience. The engines ignite, the vehicle begins to rise, and acceleration pushes the astronauts back into their seats. The rocket is moving through an atmosphere that becomes increasingly difficult to push through as its speed increases, and eventually it reaches what engineers call maximum dynamic pressure, or max Q. This is the point where the combination of speed and atmospheric density creates the greatest aerodynamic stress on the vehicle. The engines can temporarily throttle down during this period to reduce the load on the structure. Once the rocket climbs higher, the atmosphere becomes thinner, the pressure drops, and the vehicle continues accelerating. Eventually, the sky transitions from blue toward black, and the crew is no longer looking at the atmosphere from below. They are moving through space. But reaching orbit does not mean the Mars journey has begun in the way most people imagine. Under the Starship architecture described in the original material, the crew vehicle would need to be refueled in orbit before making the major departure toward Mars. That would require additional tanker launches, rendezvous operations, and the transfer of propellant in space. In other words, the crew could already be in orbit around Earth, while still being only partway through the process of leaving Earth. The actual interplanetary journey would begin only after this additional logistical challenge had been completed. It is a good example of why Mars missions are so difficult. Solving one problem often reveals another problem sitting immediately behind it. Eventually, though, the vehicle would perform its departure burn and begin moving onto its trajectory toward Mars. This is the moment when Earth would genuinely start to recede. At first, the change would not be dramatic. The planet would still look enormous compared with everything else around it. But as the spacecraft continued outward, Earth and the Moon would become smaller together, and eventually Earth would stop looking like the huge world astronauts are accustomed to seeing from low Earth orbit. It would become another object in the blackness. Astronauts have already described the powerful psychological effect of seeing Earth from space, something often called the overview effect. Borders disappear from orbit, and the planet looks unified and remarkably fragile. A Mars crew would experience that perspective under circumstances that are far more extreme, because they would not simply be looking at Earth from above, they would be leaving it. That is when the psychological side of the mission starts to become just as important as the engineering. A 7-month journey is long enough for the excitement of launch to disappear and be replaced by routine. The crew would wake up, work, maintain equipment, exercise, eat, communicate with Earth, sleep, and repeat the cycle. The destination would be extraordinary, but the day-to-day experience would still contain plenty of repetition. There is no changing scenery in the normal sense. There is no opportunity to go for a walk outside. There is no restaurant, park, hotel, or spare room where you can simply disappear for a while. The same small group of people would occupy the same spacecraft for months, while knowing that the people they care about are millions of miles away. Research from isolated environments on Earth gives us some idea of what this can do to people. Antarctic winter overcrews, submarine crews, and astronauts have all provided researchers with information about prolonged isolation and confinement. Sleep can become fragmented, attention can narrow, irritability can increase, and the ability to interpret the emotional signals of other people can deteriorate. Researchers have also observed what is sometimes described as a third-quarter effect, in which morale and motivation can decline during the latter part of a long isolation period. The initial excitement has disappeared, but the end still feels far away. A Mars crew would have to deal with these psychological effects, while knowing that their ability to escape the environment is essentially non-existent. This is why a Mars crew would have to be selected for more than technical ability. The astronauts would need to function as a team for years under conditions where mistakes could have serious consequences. They would have to make decisions without immediate guidance from Earth, manage disagreements inside a confined environment, maintain their own motivation, and continue working when the mission stopped feeling exciting. A Mars expedition would therefore be as much a psychological experiment as an engineering one. The spacecraft could be perfectly designed, but if the people inside it cannot function together, the mission still fails. Then there is the threat that does not care how calm or experienced the crew is: radiation. On Earth, we are protected by two enormous systems that are easy to overlook precisely because they are always there. Earth's magnetic field deflects much of the charged particle environment produced by the Sun, while the atmosphere provides another major layer of shielding. Human beings evolved underneath these protections. When astronauts travel beyond them, the radiation environment becomes significantly more serious. The danger is especially unsettling because it is invisible. There is no smell, no sound, and no sensation, telling you that energetic particles are passing through the spacecraft and interacting with your body. One source is solar energetic particles produced during events such as solar flares and coronal mass ejections. These particles can reach a spacecraft after an event, potentially giving a crew only a limited amount of warning. A major solar particle event could deliver a dangerous dose of radiation over a relatively short period, which is why mission concepts include heavily shielded areas where astronauts could take shelter. The Apollo astronauts benefited from fortunate timing because major solar particle events occurred during the Apollo era without coinciding with a crewed mission in a way that would have exposed astronauts during transit. A 7-month trip to Mars creates a much longer period in which the crew could encounter such an event. Galactic cosmic rays are an even more persistent challenge. These are extremely energetic particles originating from violent astrophysical events, including supernovae, neutron star collisions, and environments associated with active black holes. They can travel across enormous distances before encountering a spacecraft, and when they strike the material around the crew, they can produce secondary particles that complicate the shielding problem. Simply adding more material is therefore not always a perfect solution. The type of material matters, and hydrogen-rich materials, such as water and polyethylene, are particularly interesting because they can provide useful shielding without creating as many problematic secondary particles as some heavier materials. The Curiosity rover gave researchers an important opportunity to measure the radiation environment during a real journey between Earth and Mars. Its radiation assessment detector collected data during its roughly 8-month cruise and then continued taking measurements on the Martian surface. The results demonstrated that the interplanetary environment represents a significant radiation exposure compared with what astronauts experience in low Earth orbit. Mars itself also provides much less protection than Earth because it lacks a global magnetic field and has only a thin atmosphere. That means the radiation problem does not end when the spacecraft lands. The crew would continue receiving elevated exposure while living and working on the surface. And the concern is not limited to cancer risk later in life. Researchers have also investigated how deep space radiation could affect the nervous system. Experiments involving rodents exposed to simulated galactic cosmic ray environments have found changes in areas associated with memory, decision-making, anxiety, and other cognitive functions. Those findings cannot simply be transferred directly to humans, and researchers are careful about making that leap, but the underlying radiation physics remains a serious concern. High-energy heavy ions can produce complicated damage in biological tissue, including DNA and neural tissue, and some of that damage is difficult for cells to repair cleanly. For a crew that has to remain mentally sharp throughout a multi-year expedition, that possibility is particularly important. One obvious way to reduce radiation exposure is to reduce the amount of time spent in deep space. If a journey could be shortened from roughly 7 months to something closer to 3 months, the crew would spend far less time exposed to the interplanetary radiation environment. That is why faster propulsion is not merely an issue of convenience. A faster spacecraft could directly change the health risks of the mission. It could also reduce the amount of food, water, and other supplies the crew would need to carry for the journey. But faster travel requires more capable propulsion, and more capable propulsion creates its own engineering challenges. Once again, the Mars mission becomes a chain in which every problem connects to several others. The same is true of the return trip. Reaching Mars is only half of the mission, and the planets do not simply wait for the crew to finish exploring. Earth and Mars continue moving around the Sun. The crew would have to arrive during a period when a return trajectory is possible, and that can mean waiting on Mars for a long time before the geometry is favorable again. The result could be a mission lasting roughly 2.5 to 3 years in total, depending on the exact architecture and timing. 7 months getting there, a potentially very long stay while waiting for the return opportunity, and another roughly 7 months coming back. That is a completely different category of human expedition from anything we have attempted before. The psychological implications of that timeline are enormous. A person could leave Earth and not return for years. During that period, everything happening on Earth would continue without them. Family members would age, relationships would change, people would move, technology would advance. The crew would experience those changes almost entirely through delayed communication. They would not be visiting another country or even spending a year on an isolated research station. They would be living on another planet while separated from Earth by a distance so large that even a message traveling at the maximum possible speed would require minutes to cross it. And yet the reason Mars remains so compelling is that the planet has just enough similarities to Earth to make the idea of human presence imaginable. A Martian day is about 24 hours and 37 minutes, surprisingly close to the length of an Earth day. Mars has seasons because its rotational axis is tilted at an angle similar to Earth's. It has a rocky surface, polar ice, water locked into ice and minerals, and a thin atmosphere made primarily of carbon dioxide. Those similarities are part of what makes Mars feel like a possible second destination, rather than an utterly inaccessible alien world. But the differences are what would make living there so difficult. A human being standing on Mars would still be living inside an artificial environment. The thin atmosphere would not provide the same protection or conditions that Earth's atmosphere does. The planet's lack of a global magnetic field means the surface is exposed to a radiation environment very different from Earth's. Water exists, but not in the abundant, easily accessible liquid form that makes terrestrial life possible. Everything the crew needs would have to be carefully managed. The habitat would have to maintain the conditions that the planet itself does not provide. And that brings us to something that often gets lost when people talk about the first person on Mars. The most dramatic moment would probably be the first step, but the hardest part might be everything that happens after the cameras stop paying attention. The crew would need to live there. They would need to work there. They would need to maintain their habitat and equipment. They would need to monitor their health. They would need to manage radiation exposure. They would need to deal with the same interpersonal problems they had during the journey. except now they would have an entire planet outside the habitat instead of the spacecraft around them. The surface would look enormous, but the crew's actual safe living environment would remain extremely limited. This is why the idea of a Mars mission is so much more complicated than simply building a rocket powerful enough to get there. The rocket only solves the first part. After that, you need a spacecraft capable of supporting people for months, a system for protecting them from radiation, an approach to communication that accepts the unavoidable delay, a crew that can tolerate years of isolation, a landing system, surface infrastructure, supplies, and eventually, a way to get everyone back. Every one of those pieces has to function together. A failure in any one of them can threaten the entire mission. The strange thing is that none of these challenges make Mars less interesting. They make it more interesting. Because the question is no longer simply whether humans can reach another planet. We already know that machines can travel there. The question is whether a human being can remain alive, healthy, capable, and psychologically stable while doing it. Can we create an artificial environment capable of replacing everything Earth provides naturally? Can we protect a crew from the radiation of deep space? Can we maintain a small team for years without the normal social escape routes people have on Earth? Can we make the crew independent enough to solve problems when Earth is too far away to respond immediately? And can we bring them home? Those are the questions that turn Mars from a destination into a genuine test of human capability. The first human Mars mission would not simply demonstrate that we can build a bigger rocket. It would demonstrate that we can create an entire artificial ecosystem around a handful of people and keep that system functioning across millions of miles and years of time. And perhaps the most interesting part is that the journey would change the way the crew sees Earth. From the surface of Mars, Earth would not look like the enormous world we experience from the ground. It would be another point in the sky. The crew would know exactly what it was, but its physical size would no longer match its emotional importance. Everything they had ever known would be compressed into that tiny, distant object. That would make the overview effect far more profound than anything experienced in low Earth orbit. From orbit, Earth looks fragile. From Mars, Earth would look impossibly distant. That distance could make ordinary things feel extraordinary. The atmosphere that we normally never notice would become something precious. The ability to walk outside without a pressure suit would become extraordinary. The presence of liquid water across the surface would seem almost unbelievable. Being able to speak to someone without waiting for a signal to cross millions of miles would feel like a luxury. Earth would suddenly appear not as an ordinary background to human existence, but as the incredibly unusual environment that it actually is. And eventually, if the mission works, the crew would have to turn around and begin the return. Mars would become the place they were leaving behind, just as Earth had been months earlier. The same orbital mechanics that dictated their departure would determine when they could go home. The spacecraft would have to leave Mars, enter the correct trajectory, and begin another long period of interplanetary travel. The radiation exposure would continue. The communication delay would remain. The crew would still be confined together. But psychologically, something would have changed. They would no longer be traveling toward an unknown destination. They would be traveling toward Earth. As Earth began growing larger again, the experience could become almost the reverse of the outbound journey. A tiny point would become a recognizable world. The blue would return. The clouds would become visible. Eventually, the planet would stop looking like a distant object and start looking like a place again. The crew would have spent years away, but the planet they were returning to would still be the same world that launched them. And perhaps that is the strangest thing about imagining a journey to Mars. We tend to think the story is about leaving Earth and reaching another planet, but the deeper story is about how much Earth matters once you have left it. You only understand how unusual a place is when you have experienced its absence. Mars would make that absence impossible to ignore. It would reveal how much of human life depends on conditions we rarely think about, because Earth provides them continuously and effortlessly. So when people imagine the first human being on Mars, the image that usually comes to mind is a spacesuited astronaut standing on a red landscape. It is an extraordinary image, but it is only the final visible moment of a much larger story. Behind that photograph are years of preparation, a carefully timed launch window, an enormous rocket, orbital refueling, months of travel, radiation exposure, communication delays, psychological isolation, a landing on another world, a potentially long wait for the return opportunity, and then another 7 months of travel back toward the planet where everything began. The first footprint on Mars would therefore represent much more than the first time a human touched another planet. It would represent the first time human civilization had successfully carried a small group of people through an environment where almost nothing was naturally provided for them, and brought them safely to another world. It would be a demonstration that humans can take the systems that Earth normally supplies for free and recreate enough of them inside machines to survive somewhere else. That is what would really happen on a journey to Mars. It would not be one continuous adventure. Most of the journey would probably be routine, repetitive, carefully controlled, and sometimes incredibly boring. But underneath that routine would be an extraordinary reality. Every ordinary day would be taking place millions of miles from Earth, inside a vehicle whose walls were separating the crew from a vacuum and from radiation, with no possibility of simply stepping outside or going home. The destination would be one of the most familiar objects in human imagination, yet reaching it would require the most complicated human expedition ever attempted. And if the crew eventually stepped onto the Martian surface, they would finally understand something that is impossible to understand from Earth alone. Mars would no longer be a bright red object in a telescope. It would be somewhere they had actually been. The journey would have transformed a distant world into a physical place beneath their feet. But behind them would be Earth, still moving around the sun, still covered in clouds, still carrying every human story that came before them. And from that distance, perhaps the most remarkable thing would not be how strange Mars looks. The journey does not become easier once the spacecraft is finally on its way to Mars. In some respects, this is when the real test begins, because everything that had to happen on Earth to make the mission possible has now been compressed into a sealed vehicle moving through an environment that offers almost no margin for error. There is no maintenance crew waiting outside the spacecraft, no hospital that can be reached in an hour, and no possibility of simply turning around because someone has changed their mind. The crew has to keep the vehicle operating, keep themselves healthy, manage their supplies, monitor the environment around them, and prepare for a destination that is still months away. The spacecraft becomes their workplace, bedroom, laboratory, shelter, and entire world at the same time. And unlike living on the International Space Station, where astronauts remain relatively close to Earth and can receive rapid assistance compared with a Mars mission, a crew traveling between planets has to accept that many problems will have to be solved locally. The journey is therefore not just a matter of enduring 7 months inside a spacecraft. It is a continuous exercise in maintaining a functioning human environment, while everything outside that environment is actively trying to make human life impossible. One of the strangest parts of that experience would probably be how repetitive it becomes. The launch is extraordinary. The departure from Earth is extraordinary. The first days of watching the planet recede are extraordinary. But eventually the view outside the window changes very little, and the crew has to settle into routines. They wake, eat, exercise, perform maintenance, conduct experiments, communicate with Earth, check systems, complete scheduled tasks, and sleep. Then they do it again, and again. The spacecraft is moving incredibly quickly across an enormous distance, but from the perspective of someone sitting inside it, the journey can feel almost motionless. There is no obvious sensation of traveling at extraordinary speed because there is nothing outside the vehicle that provides the familiar visual cues of motion. You do not feel yourself crossing millions of miles. You simply remain inside the same small environment while the destination slowly becomes more relevant in the mission timeline. That contrast is difficult to appreciate from Earth. We associate travel with movement, Changing scenery, arriving at places, stopping for food, stretching our legs, meeting other people, and knowing that if something goes wrong, we can usually find some way home. A Mars crew would experience almost none of that. Their entire world would remain approximately the same size, while the distance separating them from Earth became almost incomprehensibly large. That is why the design of the spacecraft matters so much. A vehicle built for a short orbital mission can be optimized around a very different set of priorities than one intended to carry people between planets. On a short mission, you can tolerate certain inconveniences because the crew knows they will soon be home. On a Mars mission, every inconvenience becomes part of a system that has to remain tolerable for months, and small problems can accumulate. A sleeping area that feels perfectly acceptable for a few nights can feel completely different after hundreds of nights. A cramped workspace that is manageable during a brief flight becomes much more significant when it is effectively your office for most of a year. Even seemingly ordinary things such as food, waste management, personal privacy, exercise, lighting, temperature, noise, and the ability to have a few moments alone become part of the engineering problem. The spacecraft is not merely transporting people to Mars. It is trying to recreate enough of the conditions required for human beings to remain functional, while removing almost every feature of the environment in which human beings evolved. That becomes especially important because the crew cannot simply rely on gravity behaving normally. Inside a spacecraft traveling between Earth and Mars, the crew would spend the transit period in microgravity. Their bodies would respond to that environment in ways that have already been observed during long stays in space. Muscles that normally work against gravity no longer have to do as much work. Bones experience less mechanical loading. Fluids shift within the body. The cardiovascular system adapts to a radically different physical environment. Astronauts on the International Space Station already have to exercise extensively to counteract the effects of long-duration spaceflight, and a Mars mission would require that discipline to continue for months. Exercise would not simply be about staying fit or looking healthy. It would be part of keeping the crew physically capable of performing demanding work when they eventually reached Mars. That transition would be particularly important because arriving at Mars does not mean immediately stepping onto a familiar surface. The crew would have spent months in microgravity and then have to operate in Martian gravity, which is only about 38% of Earth's surface gravity. That is not the same physical environment as either Earth or the weightless conditions of the journey. The crew would have to adapt again. They would need to move around in suits, work with equipment, maintain balance, perform geological or engineering tasks, and potentially respond to emergencies while operating under conditions their bodies have never experienced for such a long period. The spacecraft journey therefore creates an unusual sequence of physical transitions. First, there is the intense acceleration of launch, then months of microgravity, then arrival at another world with much weaker gravity than Earth. Every phase asks something different from the human body. And while the crew is adapting physically, the spacecraft itself has to function continuously. This is where one of the most important differences between a Mars mission and almost every ordinary journey becomes obvious. On Earth, our infrastructure is so extensive that we rarely notice how much redundancy surrounds us. If a refrigerator fails, you replace it. If a pump breaks, someone repairs it. If a computer crashes, you restart it or use another one. If a medical device fails, there may be another device nearby. A Mars spacecraft cannot assume that level of support. Every critical system has to be designed around the possibility of malfunction, and the crew has to be trained to diagnose and respond to problems themselves. Life support is at the center of that problem. The spacecraft must provide breathable air, remove carbon dioxide, manage water, control temperature, and maintain a stable environment inside the cabin. Humans are constantly changing the atmosphere simply by living inside it. Every breath consumes oxygen and produces carbon dioxide. Every person generates heat. Every activity changes humidity. Water is consumed and recovered, Waste is produced and has to be managed. These processes are ordinary on Earth because an enormous planetary environment absorbs and regulates them for us. Inside a spacecraft, they become closed-loop engineering problems. The crew is living inside a carefully controlled artificial ecosystem, and the machinery responsible for maintaining that ecosystem cannot simply be allowed to fail. Water becomes especially valuable because it is heavy, and every kilogram launched from Earth has to be carried through the entire mission. That makes recycling extremely important. On long-duration space missions, water recovery and reuse are already part of life support technology, and a Mars mission would push that principle even further. Water would have to serve multiple purposes, and the spacecraft would need to recover as much of it as practical. The same basic resource can become drinking water, hygiene water, and part of the system that supports the crew's environment. Some water may also have value as radiation shielding because of its physical properties, meaning that mission designers can potentially use supplies for more than one purpose. This is characteristic of interplanetary mission design. Almost nothing can afford to have only one job. The same logic applies to food. A Mars crew cannot simply carry an unlimited variety of fresh meals for years. Food has to remain safe, stable, compact, and practical to store. The crew would have to live with a restricted selection for a very long period, and the psychological consequences of that monotony matter as much as the nutritional ones. Food is one of the few daily experiences that can provide comfort and familiarity, which means that something as basic as what the crew eats can become part of maintaining morale. The mission is not simply trying to keep people technically alive. It has to keep them capable of working, thinking clearly, cooperating with one another, and continuing to make good decisions after months of confinement. That last part is critical, because the most dangerous moment on a long mission may not necessarily be the dramatic moment everyone imagines. It could be an ordinary day when the crew is tired, distracted, frustrated, or mentally worn down, and something small goes wrong. Long missions create the possibility of cumulative stress. A person can be perfectly capable of dealing with an isolated emergency and still struggle with the effects of hundreds of repetitive days, limited privacy, delayed communication, and constant awareness that the people they care about are millions of miles away. The crew would therefore need procedures that reduce the number of decisions they have to make under stress. Checklists, routines, scheduled rest, communication protocols, and carefully planned responsibilities are not bureaucratic details. They are ways of protecting human judgment from becoming the weakest link in the mission. And then there is the peculiar relationship the crew would develop with Earth. At first, Earth is visually dominant. It is the place they have just left, the enormous world beneath them, the source of their language, memories, relationships, and entire civilization. But as the spacecraft travels outward, the planet gradually becomes less visually significant. The crew knows exactly where it is, but seeing it becomes increasingly difficult. Eventually, Earth and the Moon are reduced to points of light. The physical distance becomes impossible to comprehend intuitively. A person can understand the number intellectually, but the human brain does not naturally experience millions of miles as a meaningful emotional quantity. Instead, the distance reveals itself through consequences, the delayed messages, the inability to have an immediate conversation, the knowledge that an emergency cannot be solved by someone simply arriving from Earth. The fact that everyone you know continues living their normal lives on a planet that is now little more than a tiny object in the spacecraft sky. Communication becomes one of the clearest reminders of that separation. On Earth, conversation is immediate. You speak, someone hears you, and they respond. Even a long-distance phone call usually preserves the rhythm of a normal conversation. Between Earth and Mars, that rhythm disappears. Depending on the planets, positions, radio communication can take minutes each way. A message might be sent, the crew might wait, the response might arrive, and by the time the exchange is complete, the original conversation may already feel like an old event. This fundamentally changes the nature of communication. Earth cannot simply talk a crew through every problem in real time. Mission control can send instructions, but the crew has to be able to operate independently. This is one of the reasons Mars exploration requires a different philosophy from low Earth orbit. The farther the spacecraft travels, the less practical direct control becomes. That independence also changes how astronauts are trained. A crew member traveling to Mars cannot simply be extremely good at one narrow task. The mission is too isolated for that. Each person would need broad technical competence, and the crew as a whole would need overlapping skills so that the loss or incapacitation of one person would not automatically eliminate an essential capability. Medical knowledge becomes especially important because a serious injury cannot simply be handed over to a hospital team. Mechanical and electrical troubleshooting become essential because the spacecraft is the only infrastructure available. Scientific expertise matters because Mars itself is the destination, and the crew may need to make observations or collect samples in ways that cannot be completely planned from Earth. Every person becomes part astronaut, part technician, part scientist, and potentially part emergency responder. This is also why the number of people on the spacecraft matters so much. A larger crew provides more skills, more social interaction, and more redundancy, but it also consumes more oxygen, water, food, and space. A smaller crew reduces those demands, but increases the consequences of losing one person's expertise or creating interpersonal conflict. There is no perfect number. Every additional person is another human being who must be supported for years, but every missing person reduces the mission's resilience. The ideal crew is therefore not simply the largest group that can fit inside the spacecraft. It is a balance between engineering constraints and human needs. The same balancing act appears in almost every part of the mission. More shielding protects against radiation, but adds mass. More supplies increase resilience, but require more propellant. More equipment expands scientific capability, but consumes space and energy. More redundancy increases reliability, but makes the vehicle heavier and more complicated. Every decision becomes connected to another decision. This is one of the reasons interplanetary travel is so difficult. The problem is not that humans lack individual technologies capable of solving individual challenges. The problem is making all those technologies work together within the unforgiving constraints of a spacecraft that has to cross the distance between worlds. Radiation remains one of the clearest examples of that problem because shielding cannot simply be treated like adding a thicker wall to a building. The radiation environment between Earth and Mars is fundamentally different from the environment on Earth's surface. The crew is outside the protective combination of Earth's magnetic field and thick atmosphere. Solar energetic particles can arrive during major solar events, while galactic cosmic rays provide a persistent background of extremely energetic particles from outside the solar system. The crew therefore needs protection from both predictable and unpredictable sources. A spacecraft can carry a designated area with greater shielding for solar events, but galactic cosmic rays are much harder to eliminate. The problem is not merely stopping particles from reaching the spacecraft. The interactions between high-energy particles and shielding materials can create secondary radiation, making the design of the protective environment surprisingly complicated. That is why materials such as water and hydrogen-rich substances are interesting in the context of spacecraft shielding. The mission already needs water, so placing it around crew areas can provide a second function. The spacecraft does not have to carry a separate pile of useless mass purely for protection if the same mass can also serve a necessary role in the life support system. This kind of dual-purpose design is one of the recurring themes of Mars mission planning. The spacecraft has to extract as much value as possible from every kilogram. The possibility of reducing travel time, therefore, becomes extremely attractive. If radiation exposure accumulates over time, a faster spacecraft could reduce the amount of time the crew spends in the deep space environment. But increasing speed is not a simple matter of adding a more powerful engine. The spacecraft has to carry propellant, accelerate that propellant, and manage the energy required to change its trajectory. A propulsion system that makes the journey faster can introduce new engineering challenges of its own. The ideal system would dramatically reduce transit time without requiring an impractical amount of mass or creating new risks for the crew. That is why propulsion research matters so much to the future of human Mars exploration. The difference between a mission that takes many months and one that takes substantially less time is not merely a convenience. It could change the radiation exposure, life support requirements, psychological burden, and overall architecture of the mission. But even with faster travel, Mars does not become easy. The spacecraft eventually has to arrive at the planet, and this introduces one of the most dangerous transitions in the entire journey. During interplanetary flight, the spacecraft is operating in a relatively predictable environment compared with the atmosphere. Near Mars, everything changes quickly. The crew must go from traveling through space to entering the Martian atmosphere, and the vehicle has to manage the enormous energy associated with that change in velocity. Mars has an atmosphere, but it is extremely thin compared with Earth's. That creates a strange middle ground. There is enough atmosphere to produce aerodynamic heating during entry, but not enough atmosphere to make landing as straightforward as it is on Earth. You cannot simply treat Mars like Earth, with less air. The spacecraft therefore has to survive the entry environment, slow down, and then transition into whatever landing architecture the mission uses. This is another area where Mars is uniquely challenging. Earth's atmosphere is thick enough to provide significant aerodynamic braking, while Mars provides much less. The vehicle has to carry or use additional systems to manage the final descent, and because humans are inside it, the margin for error is extraordinarily small. A robotic spacecraft can be designed around a limited mission objective, and can sometimes accept risks that would be unacceptable for a crewed vehicle. A human mission has to provide life support, structural protection, emergency options, and enough reliability that the crew has a realistic chance of surviving failures. The arrival itself would also be psychologically strange. Imagine spending months looking at Mars as a distant object, watching it gradually become more visible, knowing that the destination that has existed on mission schedules and computer displays for years is finally becoming physically close. For most of the journey, Mars would be little more than a destination coordinate. Then, slowly, it would become a world you can actually see. The disk would grow. Surface features would become more apparent. The reddish color that has fascinated observers for centuries would no longer be a point of light in a telescope. It would be the landscape waiting below the spacecraft. And yet, the first view of Mars would not necessarily feel like the fulfillment of the mission. The crew would still have to land. They would still have to establish their surface operations. They would still have to verify that the spacecraft and life support systems are functioning. They would have to make sure the landing area is safe enough for the crew to begin working. The journey to Mars ends only in the sense that one phase of the mission has ended. In practical terms, the crew has exchanged one dangerous environment for another. The Martian surface would immediately introduce another problem: the atmosphere. Mars has an atmosphere dominated by carbon dioxide, but its pressure is far too low for humans to breathe, and the environment outside a pressure suit would be lethal. The crew would not step out of the spacecraft and simply walk around as they would on Earth. Every excursion outside would require a suit capable of maintaining pressure and providing oxygen, while also protecting against the environment. The suit becomes a personal spacecraft. It has to allow movement, communication, thermal control, and life support, while being robust enough for physical work. And the landscape itself would be deceptively familiar. Mars has mountains, valleys, plains, polar ice, dust, rocks, and an atmosphere capable of producing weather. Its day is close to Earth's, and its axial tilt gives it seasons. These similarities are part of why Mars feels approachable. But the similarities stop at a certain point. The thin atmosphere changes how heat behaves. The low gravity changes movement. The absence of Earth's magnetic field leaves the surface exposed to a much harsher radiation environment. The dust is everywhere. The landscape may look like something a human could walk across, but the conditions make it profoundly hostile. One of the strangest aspects of Mars would be the sky. The crew would be standing beneath an atmosphere but a very different one from Earth's. There would be no familiar blue sky surrounding them in the same way. The environment would constantly remind them that they were not on Earth. Even something as ordinary as looking toward the horizon would become a psychological experience. On Earth, a horizon usually means another landscape connected to the same world, you know. On Mars, the horizon would represent a planet that no human being had ever physically walked across before the arrival of the crew. The first steps would therefore carry a significance that goes beyond the practical work of the mission. A person stepping onto Mars would be physically separated from every previous human being by more than distance. They would be standing on another planet. For the first time, a human body would be operating on a world other than Earth. Everything that had been theoretical, simulated, tested, and discussed would suddenly become physical. The ground beneath the boots would not be a laboratory surface or a training facility. It would be Mars. But the mission could not afford to become a sightseeing expedition. The crew would have objectives, schedules, equipment, and limited resources. Scientific work would be a major reason for being there. Mars preserves evidence of its own history in its rocks and minerals, and understanding that history is one of the reasons scientists are so interested in the planet. The presence of water in its past is particularly important. Mars today is cold and dry at the surface, but evidence indicates that water once played a much larger role in shaping the planet. The ancient environment was dramatically different from the one astronauts would encounter today. Understanding what happened to that earlier Mars is one of the central scientific questions surrounding the planet. The crew would therefore be working in a world that contains clues about its own transformation. They would examine rocks, study the environment, investigate geological features, and potentially search for evidence relevant to the history of water and the planet's habitability. The difference between a human mission and a robotic mission would not simply be that people can walk farther. Humans can make decisions in real time. A geologist can look at a rock, recognize something unexpected, change priorities, and decide that a particular feature deserves closer attention. A robot can perform extraordinary work, but a human presence can bring a different kind of flexibility to exploration. That flexibility comes with an enormous price. Every minute outside the habitat or spacecraft is another period of exposure to the Martian environment. Every excursion requires planning. Every piece of equipment has to be transported, maintained, and eventually brought back or abandoned. Every sample collected creates additional logistics. The crew would have to work within a carefully controlled operational framework because the planet itself does not forgive mistakes. And unlike a field expedition on Earth, there would be no simple evacuation. If someone breaks a leg on Earth, emergency teams can potentially arrive. If a vehicle fails, another vehicle can be brought in. If weather changes, a team can retreat to a nearby building or drive away. On Mars, the nearest safe shelter could be the habitat, and getting there might itself be dangerous. That means the crew's equipment would need to be designed around self-rescue. The ability to survive a problem is not enough. They need to be able to get themselves back to safety. This makes the design of the surface habitat just as important as the spacecraft that carried them there. The habitat has to create a livable environment on a planet where the natural environment is fundamentally incompatible with human life. It must provide pressure, oxygen, temperature control, radiation protection, and enough living space for the crew to spend extended periods indoors. It also has to be reliable, because the crew cannot simply step outside if something goes wrong inside. The boundary between the habitat and the Martian environment would be absolute. On one side, a controlled artificial environment. On the other, a world that cannot support unprotected human life. That boundary would probably become psychologically significant. During the first days on Mars, the crew might be fascinated by the view outside. After weeks and months, the same landscape could become strangely familiar. They would wake up and see the same general environment, work in the same habitat, follow the same routines, and occasionally go outside in suits to conduct operations. Mars would become their home in a temporary and extremely artificial sense. Yet Earth would remain the place where their lives had begun, and where their eventual return would take them. The surface stay is also governed by orbital mechanics. The crew cannot simply decide when they want to leave. The planets continue moving around the Sun while the crew is on Mars. The return opportunity depends on the relative positions of Earth and Mars, which is why the mission architecture requires such long stays. A crew may spend many months on Mars, not because there is an endless list of things to do, but because the geometry of the solar system determines when an efficient return trajectory becomes available. Once again, human schedules have to bend around celestial mechanics. That creates an unusual psychological situation. The crew would arrive knowing that they are not simply waiting a few days for the next flight home. They would be committed to Mars for a substantial period. The return date would be part of the mission architecture long before the crew ever landed. There would be a point where the journey home is still far away, even though Earth has become psychologically more important, because it represents the end of the mission. This could create another version of the isolation effects seen during long-duration expeditions. The novelty of Mars would eventually fade. The routines would become normal. The excitement of arrival would be replaced by the patience required to remain there until the correct departure opportunity. Then, eventually, the crew would leave. And the strange thing about that departure is that it would reverse the emotional direction of the entire mission. On the way to Mars, Earth became smaller. On the way home, Earth would begin to grow again. The same planet that had disappeared into the star field would slowly become a recognizable world. But before that happens, the crew would have to launch from Mars, conduct the return trajectory, and survive another long period in deep space. The return journey would therefore not simply be a replay of the outbound journey. The crew would be different by then. They would have spent months away from Earth, months in microgravity, months exposed to the psychological demands of isolation, and months operating on another world. Their bodies would have changed. Their routines would have changed. Their understanding of distance would have changed. They would be returning with memories that almost nobody on Earth could share directly. And the return would carry its own hazards. Radiation exposure would continue. The spacecraft would still have to maintain its life support environment. The crew would still have to exercise and monitor their health. Communication would remain delayed. Systems would continue to require maintenance. The fact that the destination is now Earth rather than Mars would not make the spacecraft itself any less vulnerable. Eventually, though, Earth would become larger. At first, it might simply become a brighter point of light. Then, it would become a distinguishable disk. Eventually, the familiar blue color would return. Clouds would become visible. The planet would stop looking like an astronomical object and begin looking like home again. And that might be one of the most psychologically powerful moments of the entire mission, because the crew would be seeing the same planet they left years earlier, but from a perspective that no human beings had experienced before. The final approach would also be different from the journey outward, because the crew would be coming back into the environment that humans are adapted to. The spacecraft would have to enter Earth's atmosphere at high speed, survive intense aerodynamic heating, and slow down enough for the final landing sequence. The atmosphere that had been a protective shield during the mission would now become part of the mechanism that brings the crew home. The same air that blocks much of the radiation at Earth's surface would be the medium through which the spacecraft must safely lose enormous amounts of energy. And then, eventually, the spacecraft would stop moving. For the crew, that would not necessarily feel like the end of the mission. After years of operating under strict procedures, returning to Earth would introduce an entirely new physical challenge. Their bodies would have spent a long time away from Earth's gravity. Walking under full gravity again would not simply feel like stepping onto familiar ground. It would be a physiological transition. The crew would have to readapt to the weight of their own bodies and the mechanical demands of Earth's environment. There would also be another adjustment that is difficult to quantify: the sudden return to a world full of people. After years of living inside a small crew environment, hearing voices without communication delays, seeing landscapes that stretch across enormous distances, being surrounded by buildings, traffic, vegetation, weather, animals, and ordinary human activity could be overwhelming. Earth might feel almost alien for a while. The crew would have left as people accustomed to the planet. But they would return, having experienced a perspective that fundamentally changes what the planet looks like. That is perhaps the deeper meaning of a Mars mission. The technological achievement would be enormous, but the mission would also expose something about the limits of human beings. Getting to Mars is not just a question of whether a rocket can produce enough thrust. It is a question of whether a small group of people can remain healthy, competent, cooperative, and psychologically stable while living for years inside a highly engineered environment separated from their home planet by hundreds of millions of miles. The engineering problems can be measured. The amount of propellant can be calculated. The trajectory can be modeled. Radiation exposure can be estimated. The atmosphere can be studied. The spacecraft can be tested. But some parts of the experience are much harder to reduce to numbers. What does it feel like to know that everyone you love is on another planet? What does it do to a person's mind to look through a window and see Earth reduced to a point? What happens when the excitement of exploration becomes routine? What does it feel like to stand on Mars and realize that the landscape around you has never before been touched by a human boot? Those questions are part of what makes Mars so compelling. The planet has fascinated humanity for centuries, partly because it sits at an unusual intersection between familiarity and alienness. It has seasons, a roughly Earth-like day, polar ice, a rocky surface, and evidence of water in its past. Yet it is also cold, dry, thin-aired, radioactive compared with Earth, and completely incapable of supporting an unprotected human being at its surface. It is close enough that a human mission is conceivable, but far enough away that the journey forces us to confront limitations that disappear when we think only about traveling around our own planet. The first humans to Mars would therefore not simply be travelers. They would become the first people to experience a permanent change in the scale of human geography. Every civilization in history has been confined to Earth. People have crossed oceans, deserts, mountains, and polar regions, but every one of those journeys remained within the same planetary environment. Mars would be different. The crew would cross a boundary that has existed for the entire history of our species. For the first time, humans would deliberately leave the world that produced them and establish themselves, temporarily at first, on another planet. And the strangest part is that Mars does not need to be another Earth for that to matter. It does not need forests, oceans, breathable air, or comfortable temperatures. In fact, the very hostility of Mars is what makes the achievement meaningful. A human being standing there would be standing in a place that does not naturally accommodate human life, supported entirely by technology, training, teamwork, and systems developed over generations. The suit would be keeping the person's body alive. The habitat would be creating an artificial atmosphere. The spacecraft would have carried them across the void. The radiation shielding would be reducing a danger that Earth's magnetic field and atmosphere normally hide from us. Every breath would depend on infrastructure. That makes the contrast with Earth almost impossible to ignore. Here, we walk outside without calculating the radiation environment. We breathe without thinking about oxygen production. We drink water without considering its mass as launch cargo. We sleep without monitoring carbon dioxide scrubbers. We move under gravity without needing an exercise machine to preserve our bones and muscles. We speak to someone on the other side of the planet and expect an immediate response. We can walk into a hospital. We can repair a broken machine. We can leave a building if it becomes uncomfortable. Almost every aspect of ordinary life depends on an environment so supportive that we rarely recognize it as infrastructure. Mars would strip all of that away. And perhaps that is why the journey would change the people who made it. Looking back at Earth from deep space could make the planet's apparent divisions seem very different. Political borders would be invisible. Cities would become indistinguishable at enormous distances. The atmosphere would appear as a thin layer surrounding a small world. The things that feel enormous while living on Earth could suddenly look very small against the scale of the planet itself. That does not mean the crew would return with every human problem solved in their minds. It does not mean seeing Earth from Mars would magically eliminate conflict or disagreement, but it could provide a perspective that is difficult to achieve from the surface. The crew would know, in a way almost nobody else could, exactly how fragile the connection between humans and their home world really is. And that brings us back to the original question. What would really happen during a journey to Mars? It would not be one continuous moment of cinematic adventure. Most of the journey would probably be much more ordinary than that. There would be schedules and maintenance, there would be meals and exercise, there would be conversations, experiments, repairs, sleep, boredom, frustration, laughter, mistakes, and long stretches where the spacecraft seemed to barely change at all. There would also be moments when the scale of the mission became impossible to ignore. The final departure from Earth, the first sight of Mars growing larger, the first step onto another planet. The realization that the crew is now waiting months for the right moment to leave. And finally, the sight of Earth becoming large enough to recognize again. The journey would also expose the limits of what we currently know. The radiation problem is not completely solved. Long-duration human health remains an area of active research. The psychological effects of prolonged isolation are understood better than they once were. But a crew spending years traveling between planets would still encounter conditions that no previous human group has experienced. The engineering challenges of launching, refueling, landing, surviving, and returning at this scale remain formidable. There are serious plans and ambitious technologies, but there is a difference between designing a mission on paper and demonstrating that a human crew can live through the entire sequence safely. That distinction matters. Mars is not difficult because humans have never imagined going there. Humans have been imagining it for centuries. It is difficult because imagination does not have to carry oxygen, protect DNA from radiation, recycle water, maintain a pressure vessel, repair equipment, or keep a crew psychologically functional for years. A story can take a character from Earth to Mars in a few seconds. A real spacecraft has to cross the distance one problem at a time. And every problem has to be solved while the spacecraft is already moving. That is what makes the mission so different from almost anything humans have attempted before. The crew cannot stop halfway. They cannot step outside and breathe the air. They cannot call home and wait for a rescue vehicle. They cannot postpone the launch window indefinitely. They cannot simply abandon the spacecraft and find another way to continue. The entire mission is a chain of decisions that must remain connected from Earth to Mars and back again. The spacecraft must leave Earth safely. It must reach orbit. It must potentially be refueled there. It must depart Earth on the correct trajectory. It must protect the crew during months in deep space. It must maintain life support. It must limit radiation exposure. It must survive arrival at Mars. The crew must land safely. They must operate on the surface. They must preserve their health. They must wait for the return opportunity. Then they must launch from Mars, cross deep space again, approach Earth, survive atmospheric entry, and finally return to gravity. If any part of that sequence fails badly enough, the rest of the mission may become irrelevant. That is why a Mars mission is best understood not as one journey, but as a series of environments connected by transitions. Earth is one environment, orbit is another, deep space is another, Mars is another. Then the entire sequence reverses. Every transition introduces a new set of physical and engineering conditions, and the crew has to adapt each time. The remarkable thing is that we already understand many of the individual pieces. Humans have lived in orbit for long periods. Robotic spacecraft have traveled to Mars. We have landed machines on the Martian surface. We have measured the radiation environment during journeys to Mars. We have studied the psychological effects of isolation in Antarctica and other extreme environments. We have developed increasingly capable launch vehicles and increasingly sophisticated life support systems. The pieces exist in different forms. The challenge is assembling them into one mission that can carry human beings across interplanetary space and return them alive. And that is why the question of when humans will actually reach Mars is less straightforward than simply choosing a year on a calendar. The technology has to mature. The mission architecture has to become reliable. The risks have to be reduced to a level society is willing to accept. The launch vehicle has to be capable of delivering the required mass. The spacecraft has to support the crew for years. The landing system has to work with a human payload. The surface systems have to keep people alive. And the return system has to be ready before the crew arrives, or at least be capable of supporting the crew until it is. Ambitious timelines can shift because the physical realities do not care how ambitious the schedule is. Mars will continue orbiting the Sun whether a spacecraft is ready or not. The launch windows will open and close according to celestial mechanics. Engineering problems will take as long as they take to solve. A system that works once is not necessarily a system ready to carry people across millions of miles. Human missions demand a level of reliability that changes the entire calculation, but eventually, assuming those problems can be solved, there will be a day when a crew is sitting inside a spacecraft, and Earth is once again preparing to disappear behind them. The launch will happen. The vehicle will climb through the atmosphere. Max Q will pass. The sky will darken. The spacecraft will reach orbit. The crew will wait through the complicated work of preparing for departure, and eventually, the engines will fire for the maneuver that turns the mission from an Earth-orbiting flight into an interplanetary journey. Then, Earth will begin to shrink. At first, there will still be a world outside the window. Clouds will move across the surface. The oceans will remain visible. The planet will still look enormous enough to feel close. But the spacecraft will continue outward, and the scale will slowly change. The Earth will become smaller, then smaller again. The Moon will remain nearby in the same frame for a time, and eventually both worlds will become objects in the distance. The crew will know exactly what they are looking at. They will know that every person they have ever known is somewhere on that small world. They will know that the spacecraft contains almost everything they need for the next stage of their lives. They will know that the destination is not another continent or another ocean, but another planet. And then the routine will begin. The journey will become months of controlled isolation. The crew will exercise because their bodies are no longer living under normal gravity. They will maintain equipment because machines do not care whether the crew is tired. They will manage air and water because the spacecraft has no natural environment to absorb mistakes. They will monitor radiation because there is no planetary magnetic field protecting them. They will communicate with Earth through delays that make ordinary conversation impossible. They will eat the same limited selection of food, sleep in confined spaces, work with the same people, and watch the same distant landscape through the windows. And slowly, Mars will become larger. The point of light will become a disk. The disk will become a world. The world will become a destination. Then, the spacecraft will arrive. The crew will enter the Martian environment, descend toward a surface that no human has previously touched, and finally reach the moment that has justified the entire journey. A human being will open the path between two planets, not by sending a signal or controlling a robot, but by physically standing on Mars. And after all of that, the mission will still not be over. There will be work to do. There will be scientific observations to make. There will be systems to maintain. There will be a return window to wait for. The crew will live with the same fundamental reality that defined the outbound journey. Mars is not home, and Earth is very far away. Eventually, though, the geometry of the solar system will allow the return. The crew will leave the planet they spent years preparing to reach. Mars will begin to shrink behind them just as Earth once did. The spacecraft will return to the same environment of deep space, carrying people who now have something no human being has ever had before. First-hand memories of another planet, and then Earth will begin to grow. That final approach might be one of the strangest experiences imaginable. The planet that seemed impossibly distant would gradually become large enough to recognize. The atmosphere would become visible again. The clouds would look familiar. The blue would return. The crew would know that the long journey was finally coming to an end. After the landing, the doors would eventually open, and the crew would step back into the world they left years earlier. They would have changed. The planet would not have changed nearly as much. That may be the most important thing about imagining a human journey to Mars. The technology is spectacular, but the fundamental story is surprisingly simple. Human beings are creatures built for one planet attempting to survive on another. Everything else follows from that fact. The rocket is necessary because gravity holds us here. The spacecraft is necessary because there is no breathable atmosphere between worlds. Radiation shielding is necessary because Earth normally protects us without us noticing. Life support is necessary because Mars cannot provide the conditions our bodies require. Psychological preparation is necessary because our minds evolved around other human beings, familiar environments, and the ability to return home. Mars exposes all of those dependencies. It shows us how much Earth does for us every second of every day. And perhaps that is why the first journey to Mars will not only be a story about reaching another world, it will also be a story about finally seeing our own world from the outside. Because the further you travel from Earth, the more obvious it becomes that the planet was never just the place where the journey began. It was the environment that made the journey possible in the first place. The return from Mars would be an ending, but it would also create a strange new beginning. For the crew, the experience would not simply disappear when they stepped back onto Earth. They would have spent years living with the knowledge that the planet beneath their feet was not the only world available to human exploration. They would have seen Mars at a distance through a spacecraft window, then from orbit, then from the surface. They would have walked across terrain that had existed for billions of years, without a human ever standing there before. They would have experienced the silence of another planet, the low gravity, the thin atmosphere, the enormous separation from Earth, and the constant dependence on technology that kept them alive. Returning to Earth would therefore not erase Mars from their lives. In a sense, it might make Earth feel more unfamiliar than Mars had ever seemed. That sounds strange until you think about what happens when you spend enough time away from something familiar. The things you normally take for granted become visible. On Mars, the crew would have been surrounded by reminders that Earth is different. The air would be something they had to manufacture or carry. Water would be something they had to carefully manage. Radiation would be something they could never ignore. A landscape without vegetation would surround them. The atmosphere would be too thin to breathe. The sky would look different. Gravity would feel different. Every trip outside would require a suit. Every return through an airlock would mean coming back into an artificial environment. On Earth, all of those concerns would suddenly disappear into the background again. You could walk outside without checking a pressure gauge. You could breathe without thinking about oxygen. You could stand beneath the sky without a helmet. You could travel for hours and still be on the same planet. And perhaps the most remarkable part would be how quickly ordinary Earth could become extraordinary again. The first rain after returning might be more meaningful than the crew expected. The smell of soil, the sound of wind moving through trees, the feeling of ordinary humidity against the skin, the ability to see an enormous landscape without a helmet or visor, even the simple experience of walking across uneven ground without a spacesuit could suddenly seem almost impossibly luxurious. These are not things that normally feel like technology. They are simply features of life. But after Mars, the difference would be impossible to ignore. There would also be a physical readjustment. After spending so much time in reduced gravity and microgravity, Earth's full gravitational environment would be demanding. The crew would need time and rehabilitation to regain the strength and coordination required for normal movement. Walking would no longer be automatic in the same way. Their bodies would have adapted to a different environment, and now they would have to adapt back. The journey would therefore not truly end when the spacecraft landed. Recovery would become another phase of the mission. That is one of the reasons the total duration of a Mars expedition matters so much. When people hear that a Mars mission might take 2.5 or 3 years, It is easy to imagine that the number simply represents travel time plus a stay on the surface. But the crew would experience that entire period as one continuous physical and psychological event. There would be no clean separation between the journey and the destination. The effects of the outbound flight would influence how they lived on Mars. Their time on Mars would influence how they handled the return. And the return would begin while they were still carrying the consequences of everything that had happened before it. The mission would therefore be a test of endurance as much as transportation. A spacecraft can be designed to survive a specific environment for a certain period, but a human being is not a machine that can simply be switched on and off. The crew would need sleep, nutrition, exercise, privacy, social interaction, meaningful work, medical care, and some sense of psychological stability. They would need to remain competent for years, because a mistake made near the end of the mission could be just as dangerous as one made during launch. That creates a particularly unusual challenge. In many dangerous activities, the most intense portion is also the shortest. A rocket launch lasts minutes, a difficult landing lasts minutes, an emergency can unfold quickly. But Mars travel contains long periods in which nothing dramatic happens. The danger comes from the possibility that a small problem, a gradual health effect, a maintenance issue, or human fatigue could accumulate over time. The mission therefore has to be designed not only to survive emergencies, but to prevent ordinary life from slowly becoming unsustainable. This is why routines would become so important. The crew would have schedules that might look almost boring from the outside. Exercise sessions, equipment checks, scientific work, maintenance, meals, communications, sleep, repeated again and again. But that routine would be part of the mission's safety system. The more predictable the environment is, the easier it becomes to notice when something changes. A person who suddenly sleeps badly, behaves differently, loses concentration, or begins missing routine tasks might be showing signs of a problem before the problem becomes serious. The same principle would apply to the spacecraft. A vehicle traveling to Mars cannot simply wait until something breaks. Systems have to be monitored continuously. Small changes can matter. Temperatures, pressures, power systems, life support equipment, communication systems, and propulsion systems all have to remain within acceptable conditions. The crew would spend a great deal of time maintaining systems that people on Earth normally never have to think about. Imagine waking up every morning knowing that the walls around you are not simply walls. They are the boundary between life and an environment that cannot support you. The air inside the spacecraft is not just air. It is a controlled mixture maintained by machinery. The temperature is not controlled by opening a window. Water does not arrive through pipes connected to a planet. Waste does not disappear into a municipal system. Electricity does not come from an enormous grid. Every one of those ordinary services has been recreated inside a vehicle. That is the deeper meaning of a spacecraft as a habitat. It is not just a machine that carries people. It is an artificial fragment of Earth. And the farther the spacecraft travels, the more important that artificial fragment becomes. The crew would also have to think constantly about what happens if something goes wrong. A small malfunction that would be an inconvenience on Earth could become a major operational problem in deep space. The crew would need procedures for dealing with equipment failures, medical emergencies, communication problems, radiation events, and other hazards. They would have to practice those procedures repeatedly before launch because there would be no opportunity to improvise casually once the spacecraft was millions of miles from home. Training would therefore be almost as important as the hardware itself. The crew would need to know the spacecraft intimately. They would need to understand what normal sounds and readings looked like so they could recognize abnormalities. They would need to know which systems could be isolated and which ones could not. They would need to understand how to conserve resources if necessary. They would need to be comfortable making decisions without immediate instructions from Earth. This last requirement changes the psychology of mission control as well. During missions close to Earth, ground teams can be deeply involved in every decision. On Mars, the communication delay creates a fundamental separation. Mission control can analyze data and provide recommendations, but the crew cannot simply wait for a real-time conversation during a rapidly developing emergency. The astronauts would need to act. That means Mars exploration would require a shift from the traditional idea of astronauts as highly trained operators following instructions from Earth towards something closer to independent expedition members. The crew would still be supported by enormous teams on the ground, but the distance would impose a limit that no amount of intelligence or technology can eliminate. Light itself cannot travel faster simply because humans need an answer. That delay would become psychologically strange. Imagine sending a message to someone you love and knowing that even if they respond immediately, their response may not reach you for many minutes. Imagine telling your family something important and then sitting in silence while the message travels across the solar system. You could not fill that silence with a normal conversation. You could only wait. Eventually, the delay would become ordinary. That might be one of the strangest parts of the mission. Things that would feel surreal to people on Earth would become routine to the crew. Seeing Mars outside the window would become normal. Living without gravity would become normal. Wearing a suit to go outside would become normal. Waiting for a response from Earth would become normal. Looking at Earth as a distant point of light would become normal. The human mind is remarkably adaptable. That adaptability is one of the reasons long-duration spaceflight is possible at all. But adaptation does not mean that there are no costs. The crew would have to continuously manage the difference between what feels normal and what is actually normal. Their environment would be radically abnormal by Earth's standards, yet after enough time, it would become their daily life. That could make the return especially complicated. Earth would feel familiar, but the crew's habits would have been built somewhere else. They might have spent years making decisions based on scarcity, isolation, and strict procedures. Suddenly, there would be enormous amounts of everything around them: people, food, water, space, noise, movement, information. The transition could be overwhelming, and there would be another psychological difference. Before the mission, Mars would exist primarily as an idea. Scientists could study it. Engineers could simulate it. The crew could train for it. But none of those things are the same as experiencing it. Once the astronauts returned, Mars would become a memory that only a tiny number of people on Earth shared directly. That would give the crew an unusual relationship with the planet. They would have seen geological features that had previously existed only in photographs and data. They would have touched rocks formed under conditions that have no equivalent in ordinary human experience. They would have watched the sun from another planet. They would have seen Earth from a distance so great that the entire history of humanity existed on a tiny point of light. And that perspective would inevitably influence how they understood the original question of whether Mars could ever become a second home. The answer would not be simple. Mars has some characteristics that make it more accessible than many other destinations in the solar system. Its day is close to Earth's. It has seasons. It has a solid surface. It contains water in the form of ice and within minerals. It is relatively close compared with the outer planets. But those similarities do not mean that Mars is naturally habitable. The environment would still require extensive technological support. The atmosphere would remain too thin and dominated by carbon dioxide for humans to breathe. The surface would remain exposed to a harsher radiation environment than Earth. Temperatures would be extreme, and water would not simply be available as abundant surface liquid in the way it is on Earth. So the phrase second home can be misleading. Mars is not waiting for humans with an empty city and a breathable atmosphere. It is a world that would have to be made partially accessible through technology. The human presence would initially be extremely dependent on equipment. The habitat would matter more than the landscape. The suit would matter more than the air. Life support would matter more than the environment outside. That means the first Mars base, if humans eventually establish one, would probably look less like a town and more like a carefully maintained scientific outpost. Its inhabitants would not simply arrive, unpack their belongings, and start living ordinary lives. They would be operating inside a controlled system where every major resource has to be managed. This is where the idea of living on Mars becomes very different from visiting Mars. A short mission can carry a limited amount of supplies and accept a high level of dependence on Earth. A permanent settlement would have to become progressively more self-sufficient. It would need reliable sources of water, energy, food, construction materials, and replacement equipment. It would need medical capabilities. It would need ways of repairing infrastructure. It would need to handle waste. It would need to survive periods when Earth and Mars were poorly positioned for communication and resupply. The first explorers would therefore be testing not only whether humans can survive on Mars, but whether humans can build the systems required to remain there. That distinction is enormous. A mission can succeed if it reaches Mars, performs its objectives, and returns safely. A settlement has to succeed every day afterward. If one component fails, the settlement cannot simply be evacuated. If a critical supply runs out, Earth may be millions of miles away. If the power system becomes unreliable, the consequences could spread into life support, heating, communications, and scientific operations. If a habitat is damaged, the crew may have limited options for repair. The more permanent the human presence becomes, the more complicated the infrastructure has to become. And that raises the question of what the first astronauts would actually leave behind. Their footprints would remain on the Martian surface. Equipment would remain. Landing hardware would remain. Scientific instruments would remain. Habitats and infrastructure could potentially remain for future crews. The first mission would therefore not simply be an isolated event. It could become the first layer of a human presence that grows over time. That possibility changes the meaning of exploration. The first person to reach Mars would not necessarily be the person who spends the most time there. The first crew might simply prove that the journey can be survived. Later crews could arrive with better equipment, more supplies, improved habitats, and greater knowledge. Each mission could reduce uncertainty for the next. This is how exploration has often worked. The first expedition does not solve every problem. It changes what is known. The next expedition begins with that knowledge instead of starting from zero. Mars is particularly interesting because robotic missions have already transformed our understanding of the planet before humans ever arrived. Machines have traveled across its surface, measured its environment, studied its geology, and sent back enormous amounts of data. Human explorers would not be entering a completely unknown world. They would be entering a world that machines have been studying for decades. But the difference between a robot and a human is still profound. A robot does not need oxygen. It does not need food. It does not become lonely. It does not need sleep. It can be exposed to radiation without worrying about cancer decades later. It can operate in a dangerous environment without putting a human body at risk. But a robot also lacks the adaptability of a human mind. It does not look at a landscape and experience it as a place. It does not suddenly realize that a particular rock deserves attention because something about its appearance is unusual in a way that was not anticipated. Human exploration is therefore more expensive and more dangerous, but potentially more flexible. That flexibility would be one of the strongest arguments for sending people. Mars is not just a destination for collecting data. It is a complex world with a history that scientists are still trying to reconstruct. Human beings can make decisions in the field that are difficult to encode into a pre-planned robotic mission. A person can change the plan because the evidence in front of them suggests that something unexpected is happening. But every advantage of a human comes with a cost. A person has to be kept alive. That simple fact drives almost everything about the mission architecture. A rover can be dormant during a storm. A human needs shelter. A robot can tolerate extreme temperatures that would be dangerous to a person. A human needs thermal protection. A machine can be left on Mars if it fails. A person cannot. Every scientific advantage provided by a human explorer is accompanied by an enormous life support burden. This is why the first human Mars missions will probably be highly constrained. The goal would not be to immediately recreate Earth on Mars. The goal would be to demonstrate that humans can operate safely enough to make the next mission possible. The first crew might spend a significant amount of time simply learning how the human body responds to Mars. How does long-term exposure to its gravity affect people after months in transit? How effective are the exercise systems? How does the crew adapt psychologically to living on another planet? How well do habitats maintain stable conditions? How does dust interact with equipment? How much radiation does the crew actually receive over the full mission? How reliable are the systems over years rather than weeks? Those questions matter because the first Mars crew would become part of the experiment. Not an experiment in the simplistic sense of treating astronauts like laboratory objects, but an experiment in understanding what happens when human beings are placed into a completely new environmental context for an extended period. We already know that the human body changes in space. We know that microgravity affects muscles, bones, fluids, and other systems. We know that radiation is a concern. We know that isolation and confinement can affect sleep, mood, attention, and social interaction. But a Mars mission combines these factors in a way that has never happened to humans before. The crew would experience long-duration spaceflight, deep space radiation, communication delays, Mars gravity, surface operations, and prolonged isolation as one continuous experience. That combination is what makes the mission so scientifically valuable and so difficult. And perhaps one of the biggest unknowns is what happens when you combine all those stressors at once. A crew member might handle isolation well under normal conditions, but struggle after months of radiation exposure and disrupted sleep. Another might adapt physically, but experience psychological difficulty during the long return journey. The mission cannot simply study one variable at a time, because human beings do not experience their environment that way. Everything interacts. Sleep affects decision-making. Exercise affects physical health. Physical health affects mood. Mood affects teamwork. Teamwork affects safety. Safety affects stress. Stress affects sleep. A Mars mission would therefore become an interconnected system in which the crew and spacecraft constantly influence each other. That is why the most advanced technology in the mission may not be the rocket at all. It may be the system that allows humans to continue functioning as humans. A crew cannot be treated like cargo. Cargo does not need privacy. Cargo does not need meaningful communication with family. Cargo does not need a varied schedule. Cargo does not experience loneliness. Cargo does not become bored. Cargo does not need reassurance after an emergency. Humans do, and those needs become more important the longer the mission lasts. This is also why the concept of personal space becomes surprisingly important. On Earth, privacy is often something we take for granted. You can close a door. You can walk outside. You can drive somewhere alone. You can change your surroundings. On a Mars spacecraft, the crew would be surrounded by the same people almost continuously. Even a few minutes of solitude could become valuable. The spacecraft would therefore have to be designed not just around efficiency but around psychology. Lighting could matter. Sound could matter. Sleeping arrangements could matter. The ability to communicate privately could matter. Personal objects could matter. The crew would need some connection to individual identity in an environment where almost every aspect of life is shared. And then there is the outside world. The window could become one of the most important features of the spacecraft, not because it serves a technical function, but because it provides a connection to something beyond the walls. The view would change gradually, but it would change. Earth would shrink. Mars would eventually grow. The stars would remain visible in a way that is difficult to experience from Earth's surface. The stars themselves might become strangely familiar. On Earth, the night sky is filtered through an atmosphere and affected by light pollution. In deep space, the crew would see the universe without the same atmospheric interference. But the beauty of that view might eventually become ordinary, too. The crew would still have work in the morning. There would still be equipment to inspect. There would still be meals to eat. The universe could be spectacular outside the window, while someone inside the spacecraft is worrying about a malfunctioning piece of equipment. That contrast would probably define much of the journey. The greatest view in human history might be visible outside, and someone might still be complaining about the exercise schedule. That is not a failure of the experience. It is a reminder that human beings adapt. If every moment remained overwhelming, nobody could function for years. Eventually, the extraordinary becomes routine. Mars would become the place outside. Earth would become the distant place. The spacecraft would become home. And that psychological shift could be essential to survival. The crew cannot spend 7 months constantly thinking about how far away they are. They have to live. They have to work. They have to laugh. They have to argue. And then move on. They have to establish routines and relationships. They have to make the spacecraft feel familiar enough that their minds can relax inside it. That is the strange paradox of the mission.